Okay, so let us continue our discussion of continuous functions. Let us start by recalling what we have already seen. So what we have seen is this: if f is a function of this type, where a comma b is an ordinary closed interval in R and f is continuous, then f is bounded. That means there exists a positive real number m such that the absolute values of all these function values are less than or equal to m. That's what we mean by f being bounded. And today we are going to strengthen this result by showing that not just this is true, but additionally f actually assumes a maximum value and a minimum value inside this domain itself somewhere. So for that, let us start with the definition of maxima and minima. So this will be item 965. Maxima and minima. And the definition is of course something we already know, but still let's see formally how it looks. So what we have here is a subset x of R and a function f from x into R. Although we will be considering functions of this type, but we have to see the definition in general, okay, where x need not be an interval. Also, let x naught be a point in x. We say that f attains its maximum at x naught if f of x is less than or equal to f of x naught for all x in x. This is a pretty natural definition. In fact, that's what we mean when we say maximum. Note one thing carefully, that this fact may actually be true for not just one x naught but multiple x naught. We may get confused a little bit at this point because we know that the maximum whenever it exists is unique. That's why we say the maximum, not a maximum. But you will see that yes, the maximum is unique and the maximum is f of x naught, not x naught itself. Okay, x naught is the point where the maximum value is attained by f, and that may happen at multiple points. So if it happens at some point x naught, we say that f attains its maximum at x naught. But f actually may attain maximum at some other point also. Same maximum value is same, but the points where that value is attained may be more than one. Okay, at maybe more than one places. Similarly, we say f attains its minimum at x naught if f of x naught is the smallest of all the available f values, all the f values for all x in x. Such a maximum or minimum value actually may not exist, okay, but now we are going to prove that if we have a function like this and it's continuous, then that function will have a maximum value and also a minimum value. Now there is a remark immediately after this definition which should be obvious. Still the author asks why, and the remark is just this: if a function of the type that we are considering attains its maximum somewhere, then it is bounded from above. The author asks why, but that is obvious, because if it is attaining its maximum somewhere, then there is some such x naught for which this f of x naught is the largest value, but then all the f values are bounded from above by that value. Similarly, if f attains its minimum somewhere, then it is bounded from below by some value, okay. So that of course I am not writing, so that is the remark. And now comes this improvement of the previous result that we have been talking about, and that is this next proposition. And it has a name also. It's called maximum principle. So what it says is basically this: you have to, I'm not writing the formal statement, okay, let's see what it says. You have two real numbers a and b where a is less than b, and say you have a function from the closed interval a comma b into R that is continuous. So this was also the setup for our previous result where we claimed that f is bounded. So yes, now also f is going to be bounded, but additionally now this will happen. Then f is going to attain its maximum somewhere and minimum somewhere. That is the new claim. Then f attains its maximum at some point which we will write as x max inside the domain, and its minimum at some point x mean inside this. Now before we see the proof, there is a remark, a small remark. This remark is about the name that has been given to this proposition, maximum principle. The author says it's a misnomer. It's not a very nice name. I mean, it's not a very accurate name. That's because the result involves not just maximum but minimum also. So he suggests that instead it should have been named extremum principle, which involves extreme values, which can either be a maximum value or a minimum value. So let us next see the proof. And in the proof, we are going to use our that boundedness of f, that result that we already have proved. So from in fact that itself we will write first. That's how the proof is going to begin. And that was a lemma, I think. Yeah, lemma 963. So, oh, and before that, the author mentions one thing, that we are going to only prove the existence of a point where f attains its maximum. One can similarly prove that an x mean also exists, which you will realize, I mean, it will be obvious how to go for the minimum case once you see the proof for the maximum case. So let's just see the maximum case. So this is how things are going to go. By lemma 963, there exists a real number m which is going to bound the values of f, because f is bounded. Such that for all the inputs x, you of course understand that these inequalities are equivalent to this. Okay, and we have written these inequalities in place of this because we want to use the fact now that the f values are bounded from above. They are also bounded from below, but that part we are not going to use because we have decided to show that x max exists. That other inequality should be used to show that x mean exists. Okay. So now we are going to consider the set of all these f values. Let's see how that set looks. It has been given the name E. So it is actually just nothing but all the f values for all the inputs. So because this is E and all the f values satisfy these inequalities, we immediately see one thing, that E is a subset of this closed interval. That is the first observation. And the second observation is this: E is non-empty, which actually seems obvious, but exactly why? There should be a reason for that. No? Can you see immediately what at least one element in E? Well, yeah, of course. For example, f of A is in E because you can take x equal to A. Similarly, f of B is also in E because of this reason. So now you combine these two facts and you observe this. So E is a non-empty subset of R. R because after all everything is happening inside R, that is bounded from above by M. M is an upper bound for E because of this thing. And when you see this statement, immediately what comes to your mind? Least upper bound property. We know that any non-empty subset of R which is bounded from above has a least upper bound, which we also call its supremum. In fact, the supremum thing, that thing has been defined for any subset of R, not just bounded. And let us just recall the general definition of supremum. It doesn't hurt to also recall these things when they come up in some proof or something. It helps us remember the things, okay? For any subset S of R, this is how supremum was defined. There are cases, suppose S is the empty set, S may be empty also, okay? In that case, the supremum of S is defined to be equal to minus infinity. It looks very strange, but this is how it is defined. Next comes the case where S is non-empty, and here also there will be two subcases. In one of them, S has no upper bound. No upper bound in R, of course. Then the supremum of S is defined to be equal to plus infinity. And then there is that other subcase where S is non-empty and has an upper bound. And it's not just a definition, but it's a result that in that case there exists a least upper bound, which we have defined as the supremum of the set. And in fact, this is the result which distinguishes the system of real numbers from the system of rational numbers. So anyway, so now we have this quantity which we are going to call M, and we now know that it's a real number. Okay, this fact, you see, for any subset of R, its supremum exists, but only in that case it's a real number. In other cases, it's not a finite real number. It lies outside the system of real numbers, but these are extended real numbers. Okay, so now we have this. So now how can we use this m? Let's see. We see one thing immediately. What is m? M is the least upper bound of E, which means that m is after all an upper bound of E. What are the elements of E? The functional values. So the thing that we immediately get from this is this. Okay, and our aim will now be to prove that actually this m is not just an upper bound, but m itself is an f value for some x. And when we do that, when we are able to show that, then of course f attains its maximum, and that maximum value will be m at some point. That some point can be considered as x max. There may be many x maxes, but we need to show at least one exists. Okay, so that's the next aim. So now what can we do? Now we are going to use the fact that this is the least upper bound. It's an upper bound, fine, but among all upper bounds, it's the smallest. Like this. Suppose you consider a positive integer n, any positive integer n. Then what about this number? M minus 1 over n. Obviously it is less than m. So if m is the least upper bound, it's even smaller than m, so it can no longer be an upper bound for the set E, which means that it cannot bound the set E from above. So at least one element of E has to exceed this in order to make it not an upper bound. Okay. Then this is not an upper bound for E. So at least one element of E, which of course is some f value, exists which will exceed this m minus 1 over n for some extent in the domain. And because our choice is an arbitrary positive integer, this is going to happen for every positive integer. And that way we are going to get a sequence xn. To show that this input depends on n, we have written xn. Thus, we get a sequence in our domain of f, because every such xn is going to come from a comma b, such that m minus 1 over n is less than f of xn, because that's how we are choosing these things, right? These extents. But at the same time, note also that f of xn must be less than or equal to m. Why? Because of this. Because the extents are after all domain elements, domain points. So the f values must not exceed m. M minus 1 over n is not an upper bound, but m is still an upper bound. It's also the least upper bound. And this is the place where we can use Hein-Borel theorem. But before we go to that, let us consider another thing that has happened here, which is often overlooked. There is no problem, but still let's see that actually we need the axiom of choice here, axiom of choice for the fact that xn is well defined. But why? We have already discussed something similar before also, but let us also see it now. You see, for every positive integer n, we are getting xn for which something is happening. So if you consider these steps, say let me call Sn, I know Sn denotes something else in algebra, forget about those things. Let Sn be the set of inputs x in a comma b for which m minus 1 over n is less than f of x. What we are saying here is that each such Sn is non-empty, because there is at least one xn for which that happens. So each Sn is non-empty. The axiom of choice allows us to choose one xn from each Sn. And when we do that, we get this sequence. Or in fact, strictly speaking, or more rigorously speaking, the axiom of choice implies that there exists a sequence such that the nth term is coming from Sn. Otherwise, without the axiom of choice, we would be making arbitrary choices from infinitely many sets, which would not make this function well defined, because in order for a function to be well defined, for every input n, the output xn should be a definite thing, right? So that you cannot conclude from any other axiom or anything. For that you need the axiom of choice. But fine, we have the axiom of choice and we now have a well defined sequence in a comma b. So let us now use the Hein-Borel theorem, which was, if you want, I can write the number also. Theorem 9124. What was the statement of Hein-Borel theorem? It says that a subset of the set of real numbers is closed and bounded if and only if every sequence in the subset has a convergent subsequence, converging to some point in the subset itself. So that subset in our case is a comma b. We know that it is closed, it contains all of its adherent points, and it is also of course bounded. So the sequence that we now have in this is xn. So xn will have a convergent subsequence. There exists a subsequence xnj of xn, of course, that is understood, that converges to some point inside a comma b itself, and that point we are going to denote as x max. So you can understand that this is going to be our x max. We can call it whatever we want. So in anticipation that this is going to be our point, so we have called it x max. Okay, so not only does the sequence xn have a convergent subsequence, but that has its limit inside the set itself, inside the closed bounded set. Now is the time that we are going to use the fact that f is continuous on its domain everywhere. So in particular, x will be continuous at this point also, since f will be continuous. F is continuous at x max. So by the sequential formulation of continuity, because you have got a sequence in the domain, it's a subsequence, but fine, it's also a sequence in the domain that is converging to x max, which is a point in the domain. The functional values of the sequence terms, that they also are going to give us a sequence f of x then j. That sequence is going to converge to the functional value at this point, f of x max. That is, we are going to get this limit of this as j tends to infinity is equal to this. Now we will figure out what this limit actually is by using these inequalities. Note that these inequalities are true for all n, but in particular for these nj's also they are going to be true. So note that m minus 1 over nj is less than f of x nj, which is less than or equal to n. So by the comparison principle, you know, we saw a result in the section on sequences, section or chapter, I forgot, I think it's chapter, where we called it the comparison principle, which says that if you have two convergent sequences an and bn which satisfy such inequalities between the terms, then the limits also satisfy similar inequalities. That is the comparison principle. Actually, the comparison principle itself doesn't say directly about limits, but it says such inequalities are true for limit superior, limit inferior, but ultimately it means that if you have convergent sequence, then the limits follow such inequalities. So that we are now going to do. And in doing so, we will note one more thing. What will happen if I take limits of all these terms as j approaches infinity? Let us concentrate on this nj. What is nj? xn is our original sequence, and we are saying that xnj is a subsequence of this. So by the definition of a subsequence, nj then should be a subsequence of the sequence of positive integers n, which implies a very particular thing, namely that it's a strictly increasing sequence, just like the sequence of positive integers. It is also strictly increasing. Why? Because its terms are going to be sum of the terms of this sequence of all positive integers. So as j increases, so does nj without any bound. So you are going to get this. This is what we need from this discussion. What I have said just now in order to justify this is actually not rigorous. Okay, something else is given in the text. Namely, the text says that nj is greater than or equal to j, and that is why 1 over nj will be less than or equal to 1 over j. Now, as j approaches infinity, the limit of 1 over j is 0, that we already know. So that is why by the squeeze test, the limit of 1 over nj is also 0, and this can be proved by induction. We have already proved this somewhere, right? I am not exactly remembering, but very recently we have proved this thing somewhere. So I want you to prove this by induction, and that is the actual rigorous way of concluding this. However, I also showed the somewhat vague way of concluding this, simply because sometimes this helps. It's not always possible to go through everything rigorously and then see if something happens. Okay, it will take ages. So sometimes we have to follow our intuition also. But anyway, now we have this, so we can take limits and use the comparison principle. So without further explaining why this side is going to be m, I am just simply going to write like this. I need to mention that now. For all positive integers j. So by the comparison principle, do you remember that the comparison principle only says that we have ordinary inequalities? Even if we start with strict inequality, it does not give us strict inequality. And these inequalities will imply this will be m, because obviously using the limit laws and that thing, that this converges to 0. And this is the constant sequence m, which does not change with j, m, so it converges to n. And that is why this limit is equal to m. Now, instead of using the comparison principle, you can use the squeeze test also and conclude directly that this limit is equal to m by observing that this converges to m and this of course converges to m. That's why by the squeeze test the limit is m. But anyway, now the limit is m. However, the limit is actually equal to fx max. And this is what we have been trying to do, right? Because m is an upper bound for e, all the f values. And that is why we have this. In other words, f attains its maximum at x max. Maybe there are other x maxes, maybe not. And now you of course should understand that a similar proof will give you the x mean also. For x mean, you will need to instead consider this. Let me just simply show you what you have to do. Although you may immediately see what you need to do, but let's see briefly. For f mean, no, you do not need to consider any other set. E itself has to be considered. But now, the fact that E is non-empty and bounded from below will give you an infimum of E. That infimum you may call m prime, and then using m prime in a similar fashion, you will be able to produce again a sequence. Again, you can use Hein-Borel theorem and get an f mean to be equal to this infimum of E, that is m prime. You see, just like the supremum is the least upper bound, the infimum is the greatest lower bound. So that's trying to create that sequence, you have to consider for every positive integer n, m prime plus 1 over n. Since m prime is the greatest lower bound, and this is even greater than that, so it can no longer be a lower bound. So at least one element of E will be less than this, but that element is greater than or equal to m prime. So that way you are again going to get a sequence and you will get a similar proof. Okay, so that part we are not seeing explicitly. And lastly, there is another remark also, which I am just simply going to say verbally. There are other results in other areas of mathematics with that same name, maximum principle. The author says that there are results in complex analysis, partial differential equations with this same name, involving respectively analytic functions and harmonic functions. So maybe one day we will see what those things are. So that's just it for tonight. Our next upload is this coming Tuesday. and on Tuesday let's go back to calculus. So until then, this is me, Lucifer, from a mathematical room. Have a nice night.